Hi, my name is Narit Trikasemsak, and my project this summer was interactive learning of human contribution preferences. So, as robots become increasingly common in the real world, humans will have preferences on how they want to collaborate with robots. Consider this task of clearing a table together. The human might have preferences on how they want the robot to behave. For example, they might not trust the robot to pick up the glassware because glass is fragile and therefore prefers that the robot grab the plate and that they remove the glasses. We call these the human collaborative contribution preferences. On the other hand, the robot might find silverware difficult to grasp and feel that it is more proficient at picking up the plates. We call this the robot collaborative contribution constraints. And so we generalize from that specific dinner table clearing task to a human robot collaboration in a pick and place task, where each partner has a reward function that represents how they would like to contribute to the task. Essentially, we take the preferences and constraints from before and model them as reward functions individual to each agent. And so in terms of knowledge of the reward functions, of course, we assume that the human knows the human's reward function and that the robot knows the robot's reward function. However, we also assume that the human knows the robot's reward. So the human is aware of the robot's contribution constraints. And so the task objective here is that the robot does not know the human's reward function, but seeks to learn it online through interaction with the human, which leads to our overarching research question of how should a robot learn the human's reward online through interaction in a collaborative pick and place task. And so our approach is made out of three main parts, which is goal inference, updating reward beliefs, and robot replanning, all of which is combined to create a collaborative robot that we deploy in a simulation environment where human and robot interact. And so I'm going to focus a little more on the simulation environment that we created. We built the simulation environment in PyBullet, which is a physics simulator. And essentially, we have a table. We have objects sprawled across the table on the left, two agents, a robot and a human, as well as a drop-off bin. And so this is a spatially complex environment, which essentially means that there is agent motion, so both agents can move, as well as the location of the objects mattering because of the distance from the agent and the actual drop-off goal. And so the goal really is to just pick up an object from the table and place it in the drop-off bin. And both these agents are trying to do that simultaneously in a collaboration task. So I want to talk a little more about our approach to the collaborative robot. While interacting, the robot has a hypothesis set of possible human rewards. One such hypothesis might be that the human values the duck the most out of all the objects, while another might be that the human actually values the sphere more. And so the first step in picking out a hypothesis, one specific hypothesis from the set, is goal inference. And so we use Bayesian goal inference using distances to goals as likelihood. So given the human's current location and distance from each of the objects, the robot is able to infer which object it believes the human is going to go pick up. And so from that prediction, we use Bayesian inverse reinforcement learning, as well as the objects already picked up by the human to update reward beliefs. So essentially, we pick out a hypothesis from the set mentioned before and say that this is what the robot believes the human's reward function is. And then we do value iteration using expected reward under robot beliefs. We formulate this task as a two-player Markov game, and given the state of the world, which is like the object's locations, the human and robot's location, as well as the reward belief, essentially what the robot believes the human's reward function is. We do value iteration and figure out what the most optimal action is for the robot to take to maximize the overall team reward. Now we want to evaluate our collaborative robot and figure out which robot planning algorithm is most suitable for this kind of task. And so we compared it to two baselines, which was a greedy robot and a random robot. The greedy robot acted with respect to its own individual reward function, and so tries to maximize that, and the random robot picks objects at random. We ran a pilot study with 5 participants, which is a within subject study. Each subject would complete the task 3 times with a different robot agent each time. And then we would, after each round, we would ask several qualitative questions of the human, as well as measuring the overall performance, which is essentially how much reward the team actually got from each task. And so, given that there are only 5 participants, there's a lot of inconsistency in the data, and with some fine tuning of the experiment setup, as well as the collaborative robot and a much larger sample size, we hope to get much more consistent results. But we saw that for some participants, the collaborative robot actually performed very well, much or relatively better than the other two. On average, though, it performed around the second best. And so some of the questions that we asked after each round was also about the fluency of the robot. So essentially how collaborative the human thought the robot was, how cooperative it was behaving. From this, we created a measure of fluency, and this is on the right side here, the mean fluency for each robot agent type. We also have some subjective data from the questions that we asked each subject after each round. And so these are comments that were made about the collaborative robot. And they show promise. They reflect what we want the collaborative robot to be doing. So essentially learning from what the human is doing and then doing like the, complementary collaborative tasks of that in order to maximize the team reward. This work was based on research funded by the Defense Advanced Research Projects Agency, and I also want to extend a thank you to Rachel Burson and Dr. John Dolan for running the RISC program and all their hard work in getting the program running, and as well as Professor Henny and Moni, Professor Reed Simmons, and Michelle Zhao for their guidance throughout this research project.